Specialized instruments are essential to comprehend, practice, and experiment with any branch of science. In the fields of electronics and telecommunications, hands-on experience plays a major role in learning and innovation.
Laboratories in this field rely on a wide range of tools like multimeters, oscilloscopes, and spectrum analyzers, signal generators, and many others. So these instruments help students and professionals to measure, visualize, and understand complex signals.
But building a fully equipped lab comes with a high price tag. Among all these instruments, spectrum analyzers are usually expensive. Even the basic models often exceed what startups and small labs can afford.
This project addresses that challenge by developing a cost-effective alternative, a modular and scalable spectrum analyzer, making high-frequency analysis more accessible and affordable.
Before we dive into the specifics, let me give you a simple overview of how everything works together. The signal starts at the input. This is the RF signal we are analyzing. We pass it through filters to clean up noise. Then mixers convert it to a manageable frequency through some up conversions and down conversions. Voltage controlled oscillators are used to produce the required frequencies for mixing. Then we use an ADC to convert the signal to the digital domain, and the FPGA processes this data and sends it to the touch display.
Now let's dive into the architecture and explore each part in detail, starting with the first critical step, signal filtering. To ensure accurate signal analysis, we begin by filtering out unwanted noises. For high-frequency signals, we use microstrip line filters, which rely solely on copper traces of the PCBs. This approach is ideal because at such high frequencies, the required inductance and capacitance values are too small that the physical characteristics of the PCB traces themselves can provide the necessary electrical behavior. This allows to focus on a cleaner, more precise signals before mixing begins.
After filtering, the signal goes through a series of mixers that convert its frequency to a more manageable range, making it easier to process. To generate the required frequencies for mixing, we use one of the sweeping VCOs and two fixed VCOs. All of these are implemented on 6-layer FR4 PCBs, a material typically rated for signals up to only 1 GHz. However, with careful calculated designs, we have been able to push the sweeping VCO to operate at frequencies up to 10 GHz.
At each mixing stage, the signal passes through intermediate frequency filters to suppress harmonics and unwanted frequencies. The filtered output is then digitized by a 14-bit ADC sampling at 80 megasamples per second, enabling real-time FPGA processing. The FPGA computes the RMS amplitude and maps it to frequency values. The ADC PCB presents key design challenges, including high-speed differential routing, precise impedance matching, and integration via an FMC connector to the FPGA.
After digitization, the FPGA calibrates the incoming 14-bit ADC data to scale and reduce noise by computing the squared sum of 4000 samples. This helps extract stable amplitude values for each frequency point. A control signal generator drives the RF synthesizer, programming 70 registers per step to sweep across the desired range. For each frequency, synchronized data acquisition ensures accurate readings. The calibrated results are formatted by a UART calibration module and sent to the touchscreen via UART. The sweep is visualized, and touching a spike reveals its frequency and power level instantly.
The touch display provides an interactive interface for intuitive control and visualization of spectrum analysis. Users can adjust zoom levels and input specific frequencies through a custom numpad for precise frequency band selection. A dynamic bubble visualization displays real-time frequency and power levels as users interact with the spectrum. Non-blocking UART communication ensures smooth and continuous data exchange between the control system and the FPGA. The free address-based task management guarantees seamless real-time updates to the display, enhancing user experience.
We have successfully built a modular scalable spectrum analyzer that delivers accurate results at a lower price point. The minimum resolution bandwidth is 5 MHz and can be extended to 1 MHz with the same hardware setup. As the limitation here lies in the filter bandwidth and the display rendering capabilities. The sweeping time is around 180 milliseconds for 300 points, and the maximum RF signal power it can handle is 10 dBm. Due to losses in the standalone PCB connectors, wires, and the use of non-low-loss PCB materials, the minimum detectable power is negative 30 dBm. However, with an upgrade, we can detect much lower signal power.
In this project, we were able to meet our initial deliverables, and with a small next step, it will be easy to further enhance the performance of this spectrum analyzer. So thank you for watching, and we hope our work inspires you to explore new possibilities in RF engineering.